Romberg quadrature takes the Richardson extrapolation trick and runs it again and again, building a triangular table where every new column is dramatically more accurate than the last, all from nothing but repeated trapezoidal estimates. Same combination step as before, applied over and over. That's the whole video. Instead of computing the trapezoidal rule just twice like we did for Richardson extrapolation, compute it many times, halving h every time. T1 uses 1 panel, T2 uses 2, T3 uses 4, T4 uses 8. Stack these vertically, that's column 1 of the Romberg table. Now take every adjacent pair in that column and combine them with the Richardson weights 4/3 and -1/3, exactly like before. T1 and T2 combine into R2, 2. T2 and T3 combine into R3, 2. T3 and T4 combine into R4, 2. 3 new estimates, each one order of accuracy higher. Here's the whole picture. Column 1, 4 trapezoidal estimates. Every adjacent pair merges diagonally into column 2, which is order h to the 4th. Every adjacent pair in column 2 merges again into column 3, order h to the 6th. And the last pair in column 3 merges once more into a single number in column 4, order h to the 8th. 4 raw estimates collapse into one very accurate one. Column 2 cancelled the a squared term, but its own error expansion isn't empty. It still carries an h to the 4th term with some new constant d4 plus smaller terms beyond that. Nothing stops us from applying the exact same cancellation trick one level deeper. Set up a times r of h plus b times r of h over 2, this time matching the h to the 4th coefficients instead of h squared. Because h over 2 to the 4th is 1/16th, the algebra gives weight 16/15ths and -1/15th instead of 4/3 and -1/3. Both combinations are special cases of one general recursion. Column k is built from column k-1 using the weight 4 to the power k-1. Plug in k equals 2 and you get the Richardson formula. Plug in k equals 3 and you get the formula from the last slide. Each new column is order h to the power 2k. Here's that triangle filled in for sine of x on 0 to pi over 2, where the exact answer is 1. Column 1 is only good to 2 or 3 digits. By column 4, the error is 8 zeros deep, 9 significant digits from just 4 trapezoidal evaluations. Define the integrand as an EES function, sine of x, so it can be called repeatedly at different step sizes. Loop over I from 1 to m. At each level, n doubles 1, 2, 4, 8 panels, and an inner duplicate applies the composite trapezoidal rule at that resolution. R of I. One holds the ith trapezoidal estimate. A second nested duplicate walks through columns k equals 2 up to m, and within each column, rows I equals k up to m. Every entry uses the same one-line formula. No special case for column 2 versus column 3. In Python, this is just 2 nested loops over a 2-dimensional array. The first loop fills column 0 with trapezoidal estimates at doubling resolution. The second loop fills every later column with the general recursion. Return the whole triangle, not just the corner, so the convergence of every column can be inspected. Plot the error of column 1, column 2, and column 3 on the same log-log axes. The slopes read almost exactly 2, 4, and 6, precisely the orders the algebra predicted. Every extra column costs one more row of trapezoidal work and one more line of arithmetic, and buys 2 full orders of accuracy in return. Romberg quadrature. Week 3.